Hello, everyone. My name is Garrett Chrisman. This is my MA383 midterm. That is an induction to proof, all coincided with a little example problem that we have. So at the end of the day, we aim to answer what is a proof, how is a proof, and why is a proof. And hopefully, by the end of this little video, we can answer these questions. Starting with it, proof writing, learning outside the box, as I would say. And my personal experiences, with proof writing has been solely on a high school geometry class, where we used proofs to prove various different geometric combinations that we saw. But it was obviously, I think there was a consensus that it was not the most favorite math class in high school. And I definitely didn't see myself writing any more proofs after that class and was thankful it was over. So maybe left a sour taste in my mouth back in high school. But now that we're seeing and getting introduced to more proofs, it feels that solutions are easy. But as we've kind of learned and found out that solutions are meant to show, proofs and solutions are meant to be seen as easy because the blood, sweat, and tears behind the proofs is not shown rather in the proof initially, but it's the fact that they are easy and they are easy to read and clear and concise shows the amount of blood, sweat, and tears that put into them. So it has this fake feeling that, oh, I could do that. That was really easy. However, putting your head to it, there's a little bit more thought that goes into it. And with that, the blood, sweat, and tears is all part of a process. Starting early, getting the gears turning as a part of that proof writing, proof kind of experimenting process isn't like other math classes where you're taking a double integral and there's certain steps and there's a known answer that you're going to kind of arrive at. Proof writing, it's, well, I can try this. There's a different avenue here. I have a little bit of intuition using maybe some examples that kind of makes me think this way. So there isn't one clear set way to do it. Rather, it's the process and your own skills and your own knowledge, your own intuition, in which you can kind of craft your own path to eventually work through the blood, sweat, and tears to get to this nice solution, easy solution. And kind of touching on that, SOPs have a military term, but we're so used to having the standard operating procedure going through the double derivative or any math function that we have, where proof writings are a little bit foreign. There isn't a SOP for a single proof. Rather, there's no intuitions, there's own ways of thinking for each individual and multiple ways to prove something that it isn't so clear on what the SOP to solve a certain problem is. But there are some frameworks that we can use that we're going to get into to make proof writing just a little bit easier. The proof writing wiki, crafted from tens of students before myself and used by the class. And it kind of has the 7-step format with some checks at the end, starting with developing examples, kicking the tires a little bit, seeing what works, seeing what doesn't, creating a general if-then statement. It's kind of a draft and seeing what we know, we want to show, and kind of that combination. Extracting what we know, it's very important, kind of given what our assumptions are, conditions starting off. Expanding on this because we can pull out different informations, and doing the same with what we're trying to show, what we're trying to prove. Extracting that, maybe expanding on it. What do we know about the different equations or different symbols occurring within that show statement? And then once we kind of pull out all the information we can from our initial if-then statement, we can create another if-then statement, but with all that know and show that we kind of pulled out of it, and we defined formulas and any further assumptions that we make in this if-then statement, which can really guide and give us a little bit more intuition on creating that final clean proof that we so think is so easy to see. But alongside, we're going to be working with my assigned statement and applying the proof writing wiki to how we can kind of solve this. So I'll read through it now. The power of sets is a set, or the set of all subsets in a set. For example, if set A has 1, 2, then the power of set A is denoted by PA. PA can have a set of nothing. The set A, where a set of just 1 and a set of just 2, which is the specific elements within set A. So our problem here, let A and B be sets. Use examples to determine if it is true that if PA equals power of B, then set A must equal set B. If it is true, we're going to prove the statement. If it is not, we're going to find a counterexample and prove the condition that it may be true. Restrictions on the sets, a statement is true, or maybe one side of this subset or the other. So that's our kind of a problem we're going to kind of see and use the proof writing wiki to kind of walk us through. First, develop examples. I kind of mentioned this beginning, kicking the tires a little bit. Pick an example that follows the hypothesis, kind of what we know, what we're trying to show. Pick another example that maybe doesn't satisfy this. Again, that's the kicking the tires part, making them a little harder. Kind of break the equation and see where our intuition might lead us. And then if we are able to break it, if we are able to find examples that maybe don't kind of work out the same, we're able to use that knowledge and kind of see, all right, well, now we have some examples. Why do these examples work the way that they do? And it can kind of get the ball rolling, get your gears turning about the problem at hand. So for our example we have above, we're going to start with a very simple, lightly kicking the tires, where power set of A will equal the power set of B. So letting the sets A equal 1, 2, 3 and B equal the set of 3, 2, 1. Your order doesn't matter, but the sets elements are the same. If we calculate the power of each set A and set B, I'll let you guys see those on the screen. You can see, even though maybe the order is a little different, that they have the same elements in them. So we can see that our hypothesis, if the sets are equal, that the power sets for the example is true in this specific example. But now we're going to apply it to a second example where maybe set A does not equal set B, and thus look at the power sets. The power set of set A equals 1, 2 is simply those 4 elements, like we saw in the introduction problem. But set B has not the same elements, sharing one element, but the second element is not the same as set A. And we can see the power set of A, as we might expect, have different elements within that power set. And this kind of follows a similar pattern. If the power sets are not equal, then the sets are not equal. And this follows the same kind of example and logic reasoning. But we can kind of see that the sets do not need to be equal for the statement to kind of be true here, that they're not equal. So I have a little bit of intuition going through these examples, and now we can kind of go through and create our if-then statement, which we kind of see here. So what is an if-then statement, though? So if what we know, we kind of saw it in the problem above, but what do we know? What are we given? What are our assumptions? Then what are we trying to prove? What is the ultimate goal of our proof that we are trying to make a claim against? So writing the if-then statement can be in the most granular terms is good practice, where if X is an element in A union C, then X will be an element in B union C. All right, it's good. I can easily deduce what's going on, but there are more granular terms that we can break it down to kind of better show what's going on in this if-then statement. So if X is an element A or X is an element C, then X is an element B or X is an element C. So we see here the meanings are the same, but taking out those sometimes complicated math symbols, even if it is only a union, and breaking it down so the words are a lot more precise in their terms. So looking at our if-then statement, we kind of saw it in the prompt there, but if what we know, then what we're trying to prove. So if we know the power set of A equals the power set of B, then we're trying to prove that set A is going to be equal to set B or must equal set B. So here in granular terms, we can kind of see if the power set of A equals the power set of B, then set A is equal to set B, kind of knowing what we're knowing and what we're trying to show. Pretty easy there. So this is my favorite step, extracting our know, because it is the assumption that we're basing our entire proof off of, or kind of the knowledge that we're given. It's simply the set of words between if and then, kind of what was highlighted before. I'll show you that with our example here. Power set of A equals power set of B. Simple enough, that's what we know. Not a lot to step 3, but it is my favorite. But we want to expand on this know, because the power set is not simply enough. We want to write out the definitions, the theorems, the formulas that go along or that are impacted in that that know aspect in between that if and then. So expand on the know and the math stratified terms, building off the above. So let's look at that in our example. We have the power set is often, or is obviously the largest impact there. So we wanted to define what a power set is. It's a set that includes all possible subsets of that set. And we can look at A and power that out and do the set. Every element A is a different subset in the power set of A, including this set and an empty set. And likewise with B, where every element B is a different subset in the power set of B, including B set B and an empty set. So we can kind of break this down a little bit more. If power set of A and power set of B, every subset of A must be in every subset of B if true, and extract it out with our no using the definitions of a power set, mainly being the big one. Then again, the definition of maybe a set and sets A and B. Next, we want to transfer over to my second favorite step, which is also pretty convenient. It's simply the words after your then in your if then statement. So what you're trying to prove. We're extracting that out, making it clear. All right, this is what we're trying to prove, and this is the steps we're going to be taking it. But it is important to identify that part, which is located right after the end. So crafting that if then statement is very important to make it clear, to very hone in on which part of the problem you're trying to prove. So we have extract your show, in our case, then A equals B. So taking that out, we do show that A equals B, that any subset found in A must also exist in B. Likewise, elements in B are also in set A. So here we have in word terms that A must be a subset found in B, and likewise showing equality that if they're each subsets of each other, then they can be concluded to be equal. And we're kind of, with elements, we kind of see that with sets here. So our next statement, we're going to expand on this. So we already saw we extracted the show, similar to set 4, write out those definitions, formulas and theorems for what we know given our show. So expand on that with the definitions like before. And here we're going to expand on our little example here. So using I or 1 as kind of a placeholder, if 1 is an element in set A, 1A is a sub-element in the power of A. You know this by definition, because the power set of A equals the power set of B. 1 is also, by definition, the power set and equality must be an element in power B. Thus, it also must be included in B. Here, replacing 1 with I or any number can kind of prove across. Therefore, A contains B, and vice versa, B contains A. So this is touching on the grounds of proof, but then we're kind of drawing out what we know in our show. We're knowing equality and equality both in the power sets and what we're trying to prove, which is that set A equals set B. We can kind of see the foundations of our proof starting to form, mainly with these definitions and the identity and the equations and math symbols that are included in our no as well as our show. So we have a lot of more information now. We're going to kind of go to that final step, if then statement on our second draft. So using the expansions, the definitions, we're going to rewrite the if then statement as a first and last sentence. So this is often with the terminology you've seen before in proofs. Let's set A and set B. I will show that A equals B. Or set A will equal set B. Finally concluding with, therefore, I've shown that set A equals set B is desired. So kind of setting the framework a little bit can kind of guide you on where you are in your proof and make it clear to the reader of, hey, this was easy. They just spelled it out for me. Well, maybe they didn't see that work behind the scenes, but since you put them in clear words and description being concise in your proof, you're able to make it look easy, although it may not always be so easy. So looking at our case, we're going to make another second draft. Let A and B be 2 sets. If their power sets A, the power sets of A and power set of B are equal, then A must equal B. So just try to find out a little bit. We can kind of break down the power sets and equality surrounded by sets A and B. So a clean proof. A clean proof will not always fit on a PowerPoint slide. So we can kind of read through clean proof, kind of give you an idea. Hopefully it sounds easy over this video and this PowerPoint. But we're going to be taking all of our parts that we've shown before using our initial if then statement and our no, our show, what we extracted by definitions, kind of show you why I think, or maybe I proved that if the power set of A equals the power set of B, then set A and set B must be equal. So the clean proof here we're working with above using the definition of power sets, subsets, as well as sets, and as well as equality, and we can prove this. So the clean proof. Let A and B be two sets. If their power sets, PA and PB, are equal, then A must equal B. I will prove the above true. First, the definition of a power set, P of S, for any set S is the set of all subsets in S, including an empty set and this set S. If I were to let an element X be an element in A, then by definition of subset, the subset including X is a subset of A. And by definition of power set, X is also an element of power set of A. We know that the power set of A is equal to the power set of B, given where every element of power set of A is also an element in the power set of B. Thus, if X in power set of A, then it must be in the power set of B. Again, by definition of power set, X must be then an element in B, being it was an element in the power set of B. Therefore, we can see that elements in A are going to be contained in elements of B. To prove equality, we aim to show that we aim to also prove that elements in B are also contained in A. So flipping the problem, via the same reasoning above that we just described, we can say element Y of set B and say element Y must be an element of A. Thus, elements in B are also a subset of A. Because A is a subset of B, A contains elements of B and B contains elements of A. Through the reasoning above, I've shown that A equals set B as desired. So that kind of being the clean proof. Lots of words. Hopefully it sounded easy over the PowerPoint. Maybe you didn't see the work before, or maybe you could recognize the work that was done. However, in the way it was described in maybe this formal writing was a lot cleaner. It was a lot more straightforward, a lot more concise to kind of give you the final product and the final proof. But how do we know if we have good proof? Well, let's look at nothing less than the quality control. So with quality control, look in these little check mark here at the end of the proof. Hopefully you think you're all done. Woohoo, we have a clean proof. Let's get some quality control on. So defines all variables used. Looking at our back check, use definition of a power set, definition of a set, definition of a subset, as well as elements in the set. So I think check mark, I like it. Proof uses words to explain all the algebraic transformations. That's what I was talking about, kind of pulling things out, putting them into the most granular terms, pulling them out. I try to use all the no fancy math symbols in the proof here, and hopefully that wasn't articulated over the video. So I'm gonna give it a check. Proof states clearly where I'm using the hypo and the no. We know quoted in the proof, but check it. The proof states the method or approach that I'm going to use. No specific approach was used in my proof, so this one could maybe be one to the side. However, proofs by definition of the power set were used, so maybe that was identified, but maybe some shaky ground with that one. But we can work on it and kind of correctly, or more specifically identify which specific proof is used. And again, citing all the definitions and theorems correctly and relying on the formulation. Important, because a lot of the proofs that we do are done by these definitions and theorems that were proved, theorems that were 100% and confident and true, and as well as definitions are important and also the foundation of any proof that we're going to make that's based on top of that. So making sure those are all cited by definition of X, by definition of so-and-so theorem, making sure that is clear in the clean proof. So that wraps up a little bit of introduction to proofs. I hope you learned a little bit about the proof writing wiki and its universalness use, especially when working with these introductory and kind of getting your feet wet with proofs, as well as working through a fairly simple example of proving equality, looking at power sets, and subsets, and using the proof writing wiki to do so. Again, my name is Gary Chrisman, and this is my MA383 midterm. Thank you all for watching.